All right, welcome back. This is a review of Exit Slip 12, where we spend some time graphing a rational function. To lead up to graphing, we start by finding vertical asymptotes and domain, as well as horizontal asymptote. So let's go ahead and dive in. To find the vertical asymptotes, we can just begin by setting the denominator equal to 0. In this case, the denominator is a quadratic, and it looks like it'll factor, so we can find the two vertical asymptotes in this example. So two numbers that multiply to -2 and add to 1 sound like +2 and -1. So our two vertical asymptotes will be x equals -2 and x equals 1. It's kind of nice to find those vertical asymptotes first, although it doesn't really matter the order, because then the domain is everything but those values. So based on our work right there with the vertical asymptotes, I'll go ahead and state the domain in two ways. One way to state the domain would be to say all x, such that x does not equal -2 or 1. The other option would be to use interval notation to say -∞ to -2, unioned with -2 to 1, unioned with 1 to infinity. So take your pick in terms of the notation you prefer. For the horizontal asymptote, we learned that there are three different cases. So if needed, you can go back and review the three cases to consider. But in this example, we notice that the degree of the numerator is equal to the degree of the denominator. So in that case, we really are looking for the ratio of the coefficients out front. So let me go ahead and erase this so I can scribble a little bit more clearly. The coefficient on x squared in the numerator is 2. The coefficient on x squared in the denominator is understood to be 1. Therefore, the horizontal asymptote will be at 2 over 1, or just 2. So the horizontal asymptote will be y equals 2. Cool. So pretty much what I'm going to do next is start graphing it. That's the last part of this exit slip. And to begin graphing, I'm going to place vertical lines at x equals -2 and x equals 1. And then we'll throw a horizontal line at y equals 2 so that we get a good feel about what the graph avoids, right? The asymptotes will be basically avoided. So let's go ahead and do that much for this last part. And then there's a recommendation here to get probably at least one more point to have some good understanding of where the graph sits. So the asymptotes help us know what to avoid, and then getting some actual points will just help us feel more comfortable with where the pieces go, because rational graphs are made up of pieces. So let's see, those vertical asymptotes again were -2 and 1. So those are vertical lines at -2 and 1. So I'll get those in place. So we've really created three different intervals for our pieces of the graph. You can tell by those two vertical lines. And then our horizontal asymptote, you can tell, was at 2. So I'll just go ahead and put in that line at 2. So y equals 2. Okay, so at this point, we have a couple options. The recommendation here is to find like the y-intercept. That would probably be a good idea. For example, in this middle interval, I could have a piece doing something like this, or I could have a piece doing something like that. Or technically, you can cross a horizontal asymptote in the middle of the graph, so you could even have something kind of more like that going on. So to get some clarity on that, let's just go ahead and find the y-intercept for starters. And to find the y-intercept, that's where we plug in x equals 0 to the function. So the function, there we go, again from the beginning was this 2x squared plus 5 divided by x squared plus x minus 2. So if I plug in 0 there, I'll go ahead and do it out loud on this screen. Plugging in 0 for x in the numerator would give me just 5, because the 2x squared term would become 0. Plugging in 0 in the denominator would give me just -2, since the x squared and the x term would become 0. So it looks like when we plug in 0 for x, we get back negative 5 halves. So 0, comma, negative 5 halves. Or if you prefer decimals, that's 0, comma, negative 2.5. So that gives us a good point to plot on our y-axis, so 0, comma, negative 2.5. But just that point by itself, again, is probably not quite enough to know what to do with the graph. So let's go ahead and work on finding another point or two. Let's work on the x-intercepts. In the videos prior, we've looked a little bit on the x-intercepts. If the y-intercept requires us to plug in 0 for x, the x-intercept requires us to plug in 0 for y. So I'll go ahead and make some space right here for the x-intercept or intercepts. There could be more than one. So we're going to set the whole function to 0. That whole function, again, is going to be the 2x squared plus 5 over the x squared, I think it was plus x minus 2, double check, looks good. And when you have a fraction set to 0, remember it's actually just the numerator that matters, right? Because 0 in the numerator of a fraction makes the whole fraction 0. So we can neglect the denominator. And if we keep solving here, something interesting is going to happen. I subtract 5, I divide by 2, and when I square root, remember that when you square root a negative, we would get back plus or minus the square root of negative 5 halves, but the square root of a negative is imaginary. So what's happening with these x-intercepts is that they're imaginary. So that means, right, if we are graphing on the real number plane, it actually won't cross the x-axis. Okay, and that's okay. So what that does tell me is that this piece that has the y-intercept at 0, comma, negative 2.5, it means that the graph will never basically go up like this or up like that because we just found that there are no x-intercepts. So I don't know for sure where my little peak is, but I know my little graph has to do something like this. And since it is a sketch, I'm going to let that be good enough. I know both ends must go down because if either end on that little piece went up, I would end up crossing the x-axis. And our work where we just found the x-intercept showed that there are no real x-intercepts. So that gives me a lot of confidence with that piece in the middle, and I hope that makes some sense to you too. Now, let's talk about the outsides. This won't be too hard. Again, we can plot just one more point on either side, but remember that for something to be a function, it must pass the vertical line test. So basically, let's talk about this space over here to the left of the asymptote x equals negative 2. Would you agree that the function could either be a little piece like this, right? It's going to ride up against the asymptotes, or it could be a little piece like this, where it rides up against those asymptotes. It has to be one or the other. It can't be both, because if I had both of these pieces, we wouldn't pass the vertical line test. By the same argument, on the other side of the graph, I'm either going to have a piece like this or a piece like this. And if it's unclear which it is, which it probably is, a good technique is just to snag another value of x real quick to help us know whether our point should go above or below that horizontal asymptote. So I'll walk you through that part, and then I think we'll be pretty good for a sketch of this rational function. Let's pick first on an x value on the left side of the graph. So again, this asymptote here is negative 2. So if I plug in, I don't know, let's just use x equals negative 3. If we plug in x equals negative 3 to the function, that's again going to just help me know, does my graph go above or below the asymptote? Let's find out. So the function evaluated at negative 3 will be 2 times negative 3 squared plus 5. So hopefully I have the function written down. I'm just plugging in. And then on the bottom, it'll be x squared, so negative 3 squared, plus x, so plus negative 3 minus 2. And let's see, if we keep cleaning up in the numerator, negative 3 squared is 9, times 2 is 18, plus 5 should be 23. Make sure you get same. On the bottom, I'm getting 9 minus 5. 9 minus 5 sounds like 4. So I'm getting 23 over 4. And of course, if we think through that, that'd be like 5 3/4 or 5.75. So we end up with this ordered pair, negative 3, comma 5.75. And really, that's enough right off the bat to tell me that my piece of my function on this side of the graph has got to be up here somewhere, right? The point we just found is above the horizontal asymptote. So my function is going to do something similar to that I just drew in. Again, it's a sketch. Cool. So that point was enough to help me know where that little piece belonged, whether it was above or below the asymptote. Same story on the right-hand side of the graph, to the right of x equals 1. You guys can already tell, if we just plugged in negative 3 to help us out on this side, let's just plug in a number like 2 on the other side, and I think we're going to find that it has a piece up here like this. And the only thing that tells me that is the squared nature of this function. But let's be thorough and plug it in. So let's show plugging in x equals, we said 2. I'm just going to make use of my handy whiteboard feature here and plug in 2 instead for all my x's. So if we plug in 2 in the numerator, we can tell we're going to get 2 squared is 4, times 2 is 8, plus 5 is 13. On the bottom, 2 squared is 4, and then we're basically adding 0 to that. So hey, we get a positive, particularly a positive greater than the horizontal asymptote at 2. So 13/4 would be what? That'd be like 3.25. So again, 3.25 would be a value above the asymptote. So that's a pretty decent sketch. Again, it is a sketch, so it's not totally perfect, but check your work on Desmos, and I think you'll find we did a pretty darn good job. So graphing rationals takes a little bit of time, but stick with it. You could be good at this.